Stokes' theorem is another widely used integral theorem involving our del operator. Whereas the divergence theorem pertained to an integral over a volume and a closed surface, the Stokes' theorem pertains to an integral over an open surface. So let me sketch an arbitrary surface. And it's an open surface. And it has a surface area of S. And it is surrounded by a closed curve of length C. So if we were to measure the length of this closed curve that encompasses our surface area, then it would have a total length of C. And so this is a I guess a control area. It's a imaginary area and placed in a vector field, so it doesn't affect the vector field. It's just a sort of imaginary or conceptual surface. And so this vector field is V. It could be flow of air, or it could be a electromagnetic field. Whatever it is, it's a vector. It's a vector, and it varies in space and in general time. So let me write down Stokes' theorem. Stokes' theorem states that if we integrate over our surface, n hat, which is the normal to the surface, dotted with the curl of our vector field. In other words, we're taking the component of the curl normal to our surface. So n hat is pointing out of the screen. If this surface is a plane, it need not be a plane, but I'll sketch it as a plane in the plane of your computer screen. N hat would be pointing outward from your computer screen. So we're dotting n hat with the curl of V and integrating over the area. And that is equal to the integral of V dotted with dr over the closed curve C. So dr is a small line element of C, and it is tangent to the closed curve or edge around this surface. Okay, so let's the left-hand side, if we look at the left-hand side, and I'm going to redraw my arbitrary surface. Remember, the curl relates to the angular momentum of V. And if there is circulation, say counterclockwise, then the curl will be outward, parallel to n hat. Again, remember, n hat is outward of the computer screen. And so we're looking at the component of the curl outward, and that will have a circulation at every point within the area that is counterclockwise and in the plane. So this represents the component. My little circular arrows represents the component of the curl of V parallel to n hat. And we're at each point, we're measuring that component and we're adding it or integrating over the whole surface. So this part represents the integral of that outward component of the curl over the whole surface. So it's a measure of the, I guess, the angular momentum at each point across the whole surface. So that's a way of visualizing the left-hand side. The right-hand side can be visualized as taking the component of V parallel to the edge, or tangent of the edge, tangent to the edge all around it. So when we integrate along the edge, we are adding all those tangential components around the edge as such, and we're saying that there's a net circulation of V. So this would measure the net counterclockwise circulation of V around the curve. And so Stokes' theorem states that if we integrate the component of the curl of V perpendicular to the surface, then that equals the net circulation of V around the edge of that surface. Okay, so those are two pictures to sort of depict the left-hand side and the right-hand side of Stokes' theorem. So the rest of the video, I'll derive Stokes' theorem, and in so doing, hopefully providing a little bit of insight for why these two relate. And your objective in your homework problems will be to use Stokes' theorem to derive some basic laws in physics. So the proof of Stokes' theorem actually comes from the divergence theorem, or one way of proving it comes from the divergence theorem. And remember again that the divergence theorem states that the integral over a volume of the divergence at every point in the volume, and here I'm going to use the letter U for a vector field, and that's equal to the integral over the surface enclosing the volume of n hat dotted with U all over that surface. And so this is the divergence, the general divergence theorem in 3D. There's also a 2D version, and that states that the integral over a open surface S of the divergence of our vector field. So the divergence integrated over the area of an open surface is equal to n hat, which is normal to the edge of the surface, dotted with U, dr, integrated over the closed curve around the edge of the surface. So let me draw that again. So here we have a open surface S, and it's surrounded by an edge, which is a closed curve. Of length C. So here we have, let's imagine we have a small length of that curve, dr, and n hat points perpendicular to curve C. So taking the normal component of u integrated over the curve is, or integrated over the edge of this area, is taking the flux of u leaving this surface area. So the other thing you need to know is u is a vector field perpendicular to another vector field v. Okay, so I'll show you how that works in the next couple of steps here. So let's write out this equation. So this left hand side again is the integral of the surface, and if we just write out the divergence of u in 2D, we have d by dx of the x component of u plus d by dy of the y component of u times dA, and that's equal to the right hand side, which is this closed integral around the curve of n sub x times ux, the x component of n hat, plus the y component of capital N hat times uy times ds. So this is just writing out the left-hand side and the right-hand side. Now, as I mentioned, u is perpendicular to v, so therefore v, again, is vx I hat plus vy j hat, and the x component of v is equal to the minus y component of the vector u, and the y component of v is equal to the x component of vector u. So this shows, you can, if you sort of sketch this out, you would see that u and v are orthogonal to each other, and this is how the two components relate. So if we define this, we can substitute into this equation the integral of s, again the x component of u is equal to the y component of v, and the y component of u is equal to minus the x component of v. Let me raise this to give me a little bit more room here. Okay, so if we look at the left-hand side, what you'll notice is that, so I've drawn my surface, my arbitrary surface, as in the plane of the xy plane, and so that's why I can define these components of the vectors the way I have. And what you can see is that this is the component of the curl of V. Again, the curl of V is a vector, and this represents the component of that vector in the k hat direction. Or also in the n hat direction. So, because n hat is in the k hat direction as I've sketched it here. And so this left-hand side becomes the integral over the surface of n hat dotted with the curl of V. That gives the n hat component or k hat component of the curl integrated over the area of our surface. Now the right-hand side, let me see, let's write out this right-hand side. Again, it's still the integral over the edge, our closed edge. And this can be written as Vx I hat plus Vy j hat. Running out of room here. And that's dotted with minus ny I hat plus nx j hat. So we're dotting it with a vector that's right. So hopefully you can see that this term can be also expressed as a dot product between vector v and this vector in terms of n hat, the x and y component of n hat. But this vector, of course, is not parallel to n hat because if it were, then it would be nx I hat plus ny j hat. It's in fact a vector that's perpendicular to n hat, and it's a vector, it's also a unit vector, which is tangent, or it's perpendicular to n hat, and therefore tangent to our curve. So t hat is equal to minus ny in the I hat direction plus nx in the j hat direction, right? So if this were nx and this were ny, then the x and y components of t hat would be switched. They would be functions of nx and ny, but they would be switched as I've shown here. And so, right, so that was the right-hand side. And this can be written as the integral, again, over the closed surface C as vector v dotted with t hat. Oops. I'm now noticing I'm making mistakes here. Let's see. So we were integrating over the closed curve and we were integrating with respect to, well, dr represented our small infinitesimal length that we're integrating over. I have in my notes ds, but it's better to, so that's why I made that mistake. So it should be dr, and then this is dr. And t hat dot dr, t hat gives the direction of dr, dr gives the length of dr, and so we can just write this as dr as a vector. So it's a vector pointing in this direction, in the direction of t, and it has a length of dr. And so the So the right-hand side, therefore, equals the integral over the closed surface of V dotted with dr. And so we have our left-hand side of the Stokes theorem here, and that equals the right-hand side of Stokes theorem here. So we've proven, or we've derived Stokes' theorem from somewhat of a mathematical line of reasoning, but you should conceptualize it as I've sketched here. Again, we're integrating the component of the curl of a vector field over the area of an open surface, and that's equal to the net circulation of V, which is the component of V along this closed curve.